Hi, it's teardown time. We've got another linear bench power supply. It's the new Siglent SPD3303X series programmable power supply. As all new Siglent gear is, it's all the new X series. They're designed to work together and, I don't know, have a similar look and feel or something like that. But anyway, this is a $539 US street price, triple output, 220 watts or thereabouts power supply, as the model number gives it away. We're looking at 30 volts, 3 amps per channel, slightly over that actually, and a fixed voltage output here. So yes, it's a real big thumping linear power supply. None of this switch mode rubbish. It's got universal voltage input on the, well, switchable voltage input on the back here, so it doesn't matter what region you're in, you can switch it to your voltage. It's Ethernet enabled, of course, for programmable functionality, and it's a precision power supply. We're looking at 1 millivolt, 1 milliamp resolution on the thing, which is order of magnitude 10 times better than the Rigol DP8302 power supply, because you have to buy, with the Rigol, you've got to buy the software option to get this the resolution that this one has. So we'll worry about how it works and all that sort of jazz later. What we want to see now is what's inside. You know what we say on here on the EEVblog, don't turn it on, take it apart. Now, it looks and feels fairly decent quality. It's got a decent carry handle on the top, and I've got no major issues with it, except the binding posts could have been a bit higher quality. I don't know, they just feel a little bit cheapish. I sort of maybe would have liked a bit better, and the holes on them for the wires are pretty darn small. Look at that. I would have preferred big, beefier holes so that you can get, you know, decent cable into these things, because this thing, you know, 3 amps, and you can parallel the thing for even higher current. So yeah, I think those holes are a bit small. I hate it when the hole's too small to poke your stuff into. Uh-oh. Not a standard width. And I'll tell you what, the binding posts don't even take 4mm banana plugs nicely. I mean, that's actually quite a loosey-goosey fit in there, and so is this one. Like this, you know, I know this is a B and C, okay? But, you know, like, that is this is not Feel-O-Vision, but that is really loose. This one that doesn't have the you know, the flared things on it, that just does not fit at all. I mean, whereas on the Rigol, for example, it fits just fine. So don't like the binding posts at all. They have a nice big clunking power switch. Beauty. None of that soft power rubbish. Alright, so let's lift the hood on this thing. Had to take the handle off the top. I like that the handle is actually screwed into the metalwork on the top there. That's very nice. It's not just like into the folded sheet metal case and then it's only held down here. So that's, you know, it gives you a lot of confidence that it's not just going to break on you. So the quality in a power supply is all about the mains transformer, the quality and brand of capacitor used, the thermals, the internal wiring, you know, construction, it's nicely loomed and things like that. So let's give it a bell. Ta-da! We're in Lake Flynn and got a nice big toroid here. Look at that. That's a monster. I like that. That's mounted vertically, but is that a shorted turn? Oh, I hope not, but anyway, we'll get to that. Nice cable loom in here. It's all, you know, it's all cable tied, held together. I don't know where that one's going. That's flapping around in the breeze there. But they've got Celastic down here. We'll take a look at the quality of the cats, but they've gone to the effort to put some Celastic down there. So here's this nice crossbar I was talking about with the anchor holes in there. So that's quite nice. And the thermals look, and in fact, it's very, very similar to another one we've looked at. I'm sure it's very similar. Anyway, the fan, of course, here, it's blowing out the back, so it's sucking the air through the heat sinks here. So our power transistors are on the side here, so that's quite nice. That's all hunky-dory. There's our mains board down there. We've got our mains wiring going over. That looks very nice. Looks like it's doing the business. We'll check out the mains, but that looks okay. It's going down to a screw terminal down there. Got a shake-proof washer on it, I'm not sure, but anyway, let's have a look at this transformer. Now, with toroidal transformers like this that they're a toroid shape, hence their name, they've got a big hole in the middle, they're a big donut, and you always mount them down with a big screw going right through the middle. And what they've got is 2 bits of sheet metal work which are connected down to the chassis down here, okay? So they're not isolated, they're electrically connected. So this plate and this place is at both at earth potential, and if you actually connect a bolt from one side to the other here to hold it in place, you actually create a shorted turn which goes through the middle of the toroid, around through the chassis and around through the other side. And that's a real trap for young players and incredibly bad design practice, but I think I might see an insulating washer right down in there. So I think they know all about that and they're doing the right thing. So it's hard to tell about the quality of the toroidal transform, but all looks okay. The wrapping all looks, hunky-dory. So I'm going to give that a pass. No problems whatsoever. Shouldn't be any, of course, hum problems and things like that, because it's not like a C-core laminate transformer, which you have to be careful of. If you don't laminate them properly, then they can actually vibrate, and that's where you get that typical, sometimes you can hear that hum in instruments that actually comes from the mains transformer. You won't get that in a toroid. So it's very nice to see a toroid there instead of toroids are generally, a higher quality solution than your traditional C-core transformer. And they've also got a rubber insulating mat in there, which is very nice, just so, no sharp bits from the metalwork or anything can actually protrude through the wrapping and pierce the windings and things like that, and also lowering its electrical isolation. So, yeah, they've done it fairly well. And there's a bit of attention to detail there. They've put some Loctite on the screws holding down the only component on this thing that moves, which is the fan and causes vibration. So excellent, but I don't see any rubber, vibration isolating washers in there. So I don't know. I haven't turned this thing on, so I don't know if it's like a temperature controlled fan. I assume it is. And I'm sorry to say, Lelon brand caps don't cut the mustard. Really? Come on. I mean, a quality power supply that costs $500 has one job, and that's to use high quality caps and provide, a long life linear power supply. Lelon, they're not the worst out there, but they're not a Panasonic. They're not a Nippon Chemicon. They're not a Nichicon. Oh, come on. They could have spent $1 or $2 more for, really top quality caps. So that's pretty disappointing. But they are 105 degrees C rated, so that's okay. LSM, I presume that's the model. I'm not going to look up the data sheet for them. And they do have the separate mains earth wire going off to the earth terminal on the front panel. That goes over to the PCB. Yes, they've got a split washer on there, so that goes over. It pretty much provides a very low impedance path through the earth terminal, and that's what you want. So they've done that decently. They haven't skimped. And if you can see down in there, they are doing temperature sensing on the heatsink. Geez, they've gobbed that up, but there we go. There's a little thermistor right down there. Bang on the heatsink, so they've got thermal overload protection. Nice. But you'd expect that. Now, I'm actually not that impressed with the mains wiring here. Why? Like, they've cable tied it together, and you might think, okay, that's all okay. They've put some, Loctite type thing on the connector so they can't wear loose and stuff like that. But the fact is, it's right up against the laser cut edge on this metal chassis, and I can feel that. That's a little bit burry, tiny burrs, but nonetheless, you can probably see actually some of the scrape marks on the edge of the wire there. Can you see that? You should be able to see that. So that's what's caused by, the laser cut edge. So that's the, like I would have put a big, insulating sleeve right over the whole bundle there. But they haven't done that, and that's just tucked down in the side like that. So it's just not safe practice. I don't like it. It's, they're probably going to get away with it, but, you know, in a quality supply, you don't want to get away with it. You want to do it properly, and that really should have a big insulating sleeve over it. Bummer. And behold, the famous Siglent rust. Look on there, I presume it's like laser cut edge here. And we've seen issues with rust in Siglent gear before. So, yeah, doesn't instill a lot of confidence, does it? If you've been watching my teardowns for a long time, you'll know I'm not a big fan of just TO220s flapping around in the breeze there, and that's what they got. Look, it's just, you know, freestanding off the board like that. I don't like it from a vibrational point of view, especially in this orientation when it's not vertical, when it's horizontal like that. Is this thing's mounted on a trolley out in some production environment or something? I've seen TO220s like that actually snap off just through vibration in a couple of months. Once again, they're probably going to get away with it, but it just shows a lack of attention to detail in that. They probably, maybe they ran out of space on the board, but I just don't like it. It gives me the heebie-jeebies. One interesting thing, here is the Ethernet and USB board. Here's the Ethernet connector down here, and you'll notice that the receiver is not, the driver's not on that board. They're actually going through this unshielded cable here, this multi-way cable, and yeah, they've got a nice sleeve on it and everything, and that goes all the way with LBJ, all the way over to the front panel where our Ethernet transceiver is down there. So yeah, see, there's our output transformers. So once again, they're getting away with that. I mean, like these are not proper twisted pairs either, like you'd get on a proper Ethernet cable. So if you wanted to do that really professionally, you'd actually put an Ethernet connector on the back here, and then you'd actually have a proper Ethernet cable running over to a matching Ethernet connector on the back here. Then you'd plug it in, and then you'd have another one coming out, and I don't know, maybe I'm being a bit nitpicky. Now you'll notice that on this heatsink here we've actually got there's our bridge rectifier, okay, input bridge rectifier, but we've got 2 power transistors on this one, whereas the one on the other side we've only got a single power transistor. There it is, down in there. Why is that the case? Well, this is a triple output power supply, so clearly they're running the 5-volt output here, or this switchable. It's not adjustable, it's switchable, so it has its positive and negative points. Anyway, they're running that one from this secondary heatsink over this side. So in theory, this the power output from here is coupled into the heatsink. For example, I'm going to assume it's channel 1 here, so that in theory you'll get less maximum power output from channel 1 than you would from channel 2, but the specs are the same, but that heatsink will actually heat up more than the other one for this one. But as long as you design that in, there's no problem with that. I'm just pointing it out. And sorry that I'm not going to take this whole thing apart. I don't really want to go to that sort of effort, so it's a bit dodgy on some of the camera angles here. Anyway, this tap on the transformer, the yellow wires, that's clearly the tap for the 3rd channel output, and there's our full wave bridge rectifier for the it uses individual diodes for that 3rd channel. So they're not putting those on the heatsink because that doesn't have the same power output requirement as channels 1 and 2. So no problems there. They can get away with that fine and dandy. By the way, our mains input board, no real problems there. There's no fusing on this board because that's part of the ISC input connector on the back panel where it's fused. They've got their isolation slots in there. You don't need common mode chokes and things like that for such a linear power supply. So yeah, that's all par for the course. No problems at all. And I said a big thumping power switch. Nice. And they've got some PTCs in there, very nice, just for this, it looks like an auxiliary winding coming from the transformer. You can see a tiny little discrete bridge rectifier there, so, that's not too shabby at all. Alright, if you're a bit disappointed about the input capacitors, well, check out the output capacitors. These are Rubicons. There you go. So that's Rubicon are a decent brand capacitor. So they've at least done why they've used Rubicons on the output and they can't use Rubicons or some better brand on the input. I don't know. But then they've mixed those up with Lelons here. Once again, you know, these Taiwanese brand. And you know, Lelon are okay. Kinda, sorta. But yeah, it's just like, why are they mixing those in? You know, like they're using Rubicon output caps. Well, why not make everything else Rubicon? Don't get it. And for those processor aficionados playing along at home, I know you're out there. We've got an STM ARM processor, so fairly grunty. So this is probably running some, you know, light Linux OS or something in a power supply. Yeah, it's like... but yeah, okay, whatever. But you know, they've got Ethernet, it's all PC controlled, blah blah, networking, the whole jazz. It's got a graphical, you know, display and interface and graphing and all that sort of stuff. So you know, you kind of sort of have to go a bit, you know, a high level OS there. There's not a huge amount of choice really, so that's fine. And they do have PCB mount fuses directly soldered on, you know, axial leaded ones, soldered onto the board down there. So they're actually doing that a few times. Well, they've got one for each channel basically, and they've got some on the front too. And they're doing that on the front panel as well right there. So once again, another resettable fuse there, PTC there, and a couple of more TO220s just flapping around in the breeze. Actually, sorry, silly me, I stand corrected. These Rubicon caps here aren't actually for the output. These look like filtering for the main power supply for all the electronics and stuff like that. Of course, the minimum output capacitance, because in an adjustable current power supply, you want the output capacitance to be absolutely minimum possible. So there's the third channel, for example, which is the fixed voltage output. Well, that one doesn't. Yeah, that one would have a current limit, I think. I don't know. I haven't actually tried it. Anyway, small amount of output capacitance, but once again, that one is a Rubicon. But there's an output for channel 2, and these are not Rubicon caps, so these are Lelons. So, yeah, there you go. They've actually got a fair bit of output capacitance there. You'll notice that the reverse protection diode there straight across the output, pretty beefy. They've got that also down here on the third channel as well. So that's common as mud. And there you go. You can just see our output current shunt resistors there. I don't know whether they're... high side or low side, but yeah, they've got two of them. Have they whacked those in parallel? Not entirely sure, but yeah, this is a precision power supply. As I said, 1 millivolt, 1 milliamp resolution, which is quite, you know, very impressive on a 30 volt, 3 amp output capable supply. So there's going to be a reasonably high-end ADC in there somewhere. Is it one of those puppies? I don't think the STM ARM processor has a high enough resolution ADC, even if it has one. And aha, this is where the magic and the performance comes from, an Analog Devices ADR7792. This is actually a pretty decent little beast. It's a 3-channel 16-bit Sigma Delta converter. It's got a built-in 4 ppm voltage reference. It's got built-in differential amplifiers and all sorts of jazz. And they've also got a ADR03. That's a pretty reasonably schmick 3 ppm 2.5 volt voltage reference as well. So they've got some decent hardware in here. So I don't doubt that it actually meets its specs and performance targets and accuracy and stuff like that. So yeah, thumbs up there. And they've got a whole bunch of sharp PC817 optocouplers there. That's to isolate all the data required. Nice. And there's one thing I don't see around the processor here, and that's a JTAG header. Is that the puppy up there, unpopulated? Perhaps. And there's all our relays in there to do the switching for our series and parallel functionality on the front, where you can join the outputs and get, you know, double the capability, so you don't have to physically wire them. You can, and then the voltage will track and things like that. So that's nice, but they're not exactly name brand relays. They use the same ones over here, and well, offhand I don't know who makes those, but whatever. And in case you don't know how linear power supplies work, when you've got a 30 volt 3 amp output range, okay, that's a lot of power. And if you've got your voltage output set to 1 volt, for example, and you've got a 30 volt input, you know, you've got to drop 30 volts at 3 amps. That's a huge amount of power, you know, dissipated in your output power transistor here and your heatsink. So if depends on the voltage range, they're actually going to switch in different taps on the transformer. So, you know, they might have like a 8 volt tap for your low voltage. So if you set your output voltage to 5 volts, it might switch it to say the 8 volt AC tap, and you don't nearly dissipate as much power in your output power transistor or your heatsink there. So, you know, when you go up to 12 volts output, they might choose a 17 volt tap or something like that. And when you go to full 30 volts output, when you set that, they might switch in 30 volt AC tap or something like that. And for those playing along at home, the switch-in trend is an IRFP 150N MOSFET. And now I remember where I've seen very similar construction here with the heat sinks. It's almost an identical arrangement, except for the toroid transformer here had a linear supply. I'll link in my Aten power supply teardown. That was a horrible, that was awful power supply, both in terms of functionality. It was awful to use, and the construction quality was pretty terrible as well. This Siglent's actually, it's quite reasonable. It's definitely streets ahead of the Aten supply, which was absolutely horrible. It used a linear transformer, but curiously, the Aten one had actually, it was a precision power supply as well, but had lots of horrible problems. But it actually had on the heatsink some thermal cutouts. It actually had thermal mechanical cutouts on there. I mean, Siglent, you don't have to have those. I guess it's just a cheaper and simpler way of doing it. Siglent are doing it electronically here. They've got, a temperature sensor directly on there, and then they can electronically shut the thing down. So that's, technically that's actually better. But, if your sensing element fails or whatever, those mechanical thermal cutouts, really old school kind of thing. But the Aten one actually used Nippon Chemicon capacitors. Go figure. And that one was really built down to a price and really shoddily constructed. So the Siglent is much better in that respect. So overall, I've got to give it a pass. It's not too bad, but there's just a few little niggly things in there. And, as I said, I would have preferred some better quality parts in there, but it is reasonably neat construction. I do believe it's going to meet its performance. It's got the ADC and the reference in there. It's doing the business, and all of the sensing, everything's on the front panel PCB down here, so we don't have to dick around with that. I'll have to link in the Rigol DP832 power supply teardown, and it actually had quite a few design issues in terms of sensing the voltage and things like that. So it actually used discrete wiring through to the front panel, whereas this actually is, being quite neat. They've actually put a bit of thought into, mounting it all on the one front panel board like that. So that's not too shabby, and there's elastic things down, and, it's certainly a pass. So, a decent quality toroidal transformer in the thing, and just let down by a few smaller touches, but generally, I guess I'm fairly happy with that. Alright, so let's power this puppy up, and maybe we can put a load on it and check out its thermal performance perhaps. So, here we go. Alright, boot in, straight into it. Look at that. Nice display on it. Love it. And that fan is actually going, but I'll tell you what, with no load on this thing, it is practically silent. So it's got to have temperature control. I expect the fan to really increase when we fully load this thing down. And there's some annoying user interface things like this. I'll have to do a separate video on using this thing. But look, you turn the voltage up, voltage setting over range. Why? Tell me that. Why flash that up? It's just stupid. Just stop at 32 volts. Just stop there. I know it's not going to get... I don't need to be warned. Give me a break. Well, I'll tell you what. I'm switching this voltage all the way through the range. I cannot hear these relays switch. I cannot hear the range switching at all. I swear, I've put my ear right up to it. Can't hear a thing. And as I said, go to plug these banana plugs in here. They really feel loosey-goosey. Doesn't instill a lot of confidence in me at all. I mean, look, I've just got, my resistor load on there, and you'll notice that the current's flapping around in the breeze. If I actually, look, put force on those banana plugs so that they're doing that. Look, I get a perfectly nice stable current. I leave them loosey-goosey and it's not making good contact. Grrr. Anyway, you'll notice that when I change this, I actually had that set to 4 volts there. If I have it set to 5, you'll notice that it actually, oh well, it doesn't do it there. Let's go to 4. It'll actually change between, so when you're turning the knob, it'll be the set voltage, okay, but then a second later after you release it, it'll be actually the physical output voltage, which is fine. I like that. But the thing is, like, they've got this huge display, right? All of this display to their advantage, but they waste all this space with this stupid timer thing. Most of the time, you're not going to use the timer. Okay, so get rid of it until you need it, and then have, set voltage, set current, and then display, maybe even a tiny font up here, set voltage, set current, and then have your big displayed, your actual output voltage and your actual output current and your actual output power. It's a power supply. You want to know this information. You want to know what you set it to. Now, in terms of thermals on this thing, I'm actually shorting the outputs, just running the thing at full pelt at the moment, but I'm having a look at the front panel here, and this, as I said, these 2 big filter caps, there's a bridge rectifier tucked away in there. It's got its own fuse. That's for the electronics, I believe, and that bridge rectifier in there, check it out, 90 odd. I'm getting a peak of like over 90 degrees for that bridge rectifier. Sorry about the glare there. Wow. That's not terrific at all. That doesn't instill a lot of confidence in me. And what I'm doing is I'm running both outputs here. I'm sort of like shorting them out, and I ran them up to 32 volts. But once again, I still don't know, without actually getting in there and start measuring stuff, probing around and dicking around, I don't know where the actual voltage taps are, because usually you'd put it like at the worst possible tap. So I could actually put it down to say 1 volt on both channels here, and then that might be near enough to sort of worst case power dissipation, because it's got to drop almost the full whatever transformer tap voltage down to our 1 volt output, and then we shorten the thing on the output. So yeah, let's give it a whirl. So this is actually really kind of hard to get, but if you have a look in there, like, sorry about the, the transformer is not black anodized, so it's not going to be an accurate temperature, so it's going to show up cool. But let's look at our silicon down there. That's our output transistor, that's the hottest, and I was getting a peak of just over 100. Yeah, there we go, 100 degrees on the power transistor. So that's pushing it, but that is worst case. It's still within margin, but yeah. And yes, by the way, at full tilt, yes, the fan does come on. It's noticeably loud, but hey, that's par for the course on these types of power supplies. Okay, I'm finally able to get the transformer taps on this thing. The output has to be on before it will switch the transformer taps. So let's go down here and clunk. Once you get to 8 volts, and switch back down from 7. There we go. So that's the first tap. And then 16, down to 15, 24, 22, so 23, 24, and that's it. There you go, 3 taps. Okay, so what I'm going to do now is use my famous power supply killer here, the BK Precision 8500 electronic load that I have managed to kill a production power supply with before. When you set it to constant resistance, you can actually get this thing to oscillate between constant voltage and constant current mode. So I've got it set to 8 volts, which is like the minimum of the tap, okay, so of the next tap. So it's actually... so we switch to the next tap. So this will be dissipating the most amount of voltage across the output power transistor. I've got my resistance set to 1 ohm here, and we'll give it a whirl. Listen to that. There we go. It's pretty horrific. It's pretty horrific. I don't see any magic smoke escaping. how to switch in the input range current as well, the transformer tap as well. I wouldn't like to leave that going all day, every day. I think it will eventually die, but yeah, let's turn that off, and it's started working again. And we can go back to, say, 1 amp constant current, for example, and switch that on. Oh, sorry. Yeah, sorry, I'd already adjusted the current here, so I've got to go in here and up the current. There we go. 1 amp. Yep, it's working a treat. And I switched it to like the 19 volt range, and it's even more violent now. Wow, it's really not liking that. But hey, it's surviving. Nothing's dying, so beauty. And I went out for a bit, came back, look at this. By default, it looks like it has a bloody screensaver. Why? This is just insanity. It's a bloody power... I assume I pushed that to get it back. It's a bloody power supply. Just leave the display there. Unbelievable. So there you have it. I hope you enjoyed the little quick look inside the Siglent SPD3303X series precision programmable DC power supply. And I'll have to do a follow-up video of this, of course, actually playing around with it. Maybe a shootout comparison with the Rygold DP832 perhaps. So yeah, well, stick around for that, even though I haven't planned to shoot it yet, but maybe I will. Anyway, if you liked it, please comment on the video, give it a thumbs up and all that sort of jazz. Discuss it on the forum, you know, follow me on Twitter and buy my merch and all that, subscribe and all that stuff I've got to say as a YouTuber to, you know, stay in business. Catch you next time.